Hello students, till now we have discussed about the AC circuits having only one circuit element, that is purely resistive, purely inductive and purely capacitive circuit. But now we are going to study about LR circuit, which contains an inductor and a resistor in series. As you can see in the diagram, we have a resistance capital R, a resistor of resistance capital R, and an inductor of inductance L are connected in series and connected to a source of alternating EMF epsilon having value epsilon naught sine omega t. So this is the circuit that we have. So the alternating EMF is epsilon is equal to epsilon naught sine omega t. Now if we assume that capital I is the current through the series circuit at any instant, we assume that capital I be the current in the circuit at any instant, then we will study pointwise about resistance and inductance. So then first, for resistor, voltage VR vector. Now this vector sign represents the phasor. That means VR is not a vector quantity, but we represent it by a phasor. So that's why we are putting VR vector sign, and here it means the phasor of voltage VR. So VR vector is equal to RI vector. That means phasor of VR is equal to R into phasor of current I across the resistance capital R. Means here VR is equal to RI across the resistance capital R. So these phasors VR vector and I vector, since it is a resistance and we know that in case of a resistance both current and EMF, alternating current and EMF, are in same phase. So phasors VR vector and I vector are in same phase or direction. That means we can show it like this. Means if this is I, then this is VR. So I and VR both are in same phase or in same direction in case of resistor, and the amplitude means the peak value. The amplitude of phasor VR is, इसको हम लिखते हैं VR naught. Now naught represents the peak value, is equal to I naught R. VR naught is equal to I naught R. This is the case for resistance. Next, the second thing we have in our circuit is an inductor. So the voltage VL vector, means the phase of VL, is equal to XL I vector. Now XL is the inductive reactance for that inductor. So this voltage VL vector is across the inductor of inductance L. That means VL is equal to XLI. Okay, this is across the coil or inductor in the circuit. Means VL vector is across the inductance capital L, and for an inductor we know that the voltage is ahead of current in phase by pi by 2, right? We know that the voltage is ahead of current. In case of inductor, voltage is ahead of current by pi by 2 radians. So the phasor VL vector lie pi by 2 radians anti-clockwise with respect to the phasor I, right? whenever we plot the phasor diagram, we have to keep in mind that the phasor VL vector lie pi by 2 radian anti-clockwise, means आगे. So radian anti-clockwise with respect to the phasor of current, that is phasor I vector. So we have to keep in mind this thing. And the amplitude of VL vector, the amplitude of VL vector is VL naught is equal to I naught XL. Okay, the amplitude is VL naught is equal to I naught XL, where XL is the inductive reactance. Now let's plot the phasor diagram for these. So current and voltage in case of resistance are in the same direction. Suppose this is the direction. So voltage is VR vector and current is I vector. Both are in same direction in case of resistance. Now in case of inductor, we know that the voltage is leading the current by pi by 2. That means जो हम voltage का phasor plot करेंगे for inductor, it will be pi by 2 ahead of that of current. So voltage will be somewhere here in this direction, such that जो angle होगा between I and this is VL vector, the phasor VL is pi by 2, because it is leading the current by pi by 2. Now if we want the resultant of these two vectors, then we can use vector laws of addition by just making parallel vectors to these, okay, and the diagonal of it will represent the resultant. So this is the resultant of the circuit. That means this is epsilon vector. This is epsilon vector, that is the net EMF or the net voltage that is connected here. Also we know that epsilon is equal to epsilon naught sine omega t. That means the angle of epsilon is omega t. So this angle is omega t from axis. This is omega t. Now if we apply the parallelogram laws of vector addition, then according to that using the parallelogram law of vector addition, the resultant epsilon vector is equal to VR vector plus VL vector. Okay, so from parallelogram law of vector addition, VR vector plus VL vector is equal to epsilon vector. So here by this law of vector addition, we can find the relation between these voltages. Now for the magnitude, we are under root V naught r ka square, that means the magnitude of VR ka square. Magnitude means the amplitude, which is the peak value, plus V naught L square plus 2 V naught r plus 2 into V naught L cos theta. Theta is the angle between the two vectors, and the angle between the two vectors is pi by 2. Since cos 90 is 0, so this term will be 0, and the value for epsilon naught will be under root V naught r square plus V naught L square. But we know that V naught r is I naught r and V naught L is I naught XL. So we will substitute these values, and then we get epsilon naught is equal to under root, this is I naught R square plus I naught XL square. That means under root I naught square, and within the bracket it is R square plus XL square. So epsilon naught is equal to I naught under root R square plus XL square, or we can write it as I naught is equal to epsilon naught upon under root R square plus XL square, where this, the denominator under root R square plus XL square, work as an effective resistance. Okay, this work as an effective resistance that is offered in the flow of current by the LR circuit and is called impedance. So impedance is the effective resistance that is offered by the circuit in the flow of AC. So here in this LR circuit, R square plus XL square is the effective resistance, so it works as impedance. That implies the impedance Z is equal to under root R square plus XL square, or we can write it as R square plus XL is omega L, then it is omega square L square. So this is the impedance of LR circuit. Now we find I naught, we find impedance, but still magnitude का resultant का direction, the direction of magnitude we haven't find yet, means the direction of that resultant vector epsilon vector. So let's see the diagram once. So this is the direction that we need, means phi. Phi is the direction that we need, means so that we can give the direction of the resultant. So for that we are going to find tan phi, and tan phi is the value of perpendicular upon base in this triangle. So this is the peak value of VL and this is the peak value of VR. So we are going to take the ratio of V naught L and V naught R. Hence to find the direction, or we can say the phase angle phi between the resultant voltage and current. For it we are going to find tan phi, and it is given as V naught L upon V naught R. That means I naught XL upon I naught R. On solving this we get XL upon R. Value of XL is omega L, so tan phi is equal to omega L upon R. This is the value of tan phi. So by this value we can give the direction of phi, means we can find the phase angle and we can give the angle at which the resultant is inclined at the current. Okay, so this is how we can completely define the resultant. The magnitude is epsilon naught, resultant का magnitude is epsilon naught, and the direction at which it is inclined with the current is phi. So we can give phi as tan inverse of omega L upon R. That's all about the AC circuit having resistance and inductance in series only. Okay, so that's all for the video. For the next video, stay tuned, be safe and keep studying. Thank you.